Good morning, good afternoon, or good evening, depending upon your perspective. This is Dr. Von Plessner. We're talking about statistics today, and we're using the Excel software package. One of the things that we're going to be doing is we're going to use the ANOVA analysis in Excel, and we're going to evaluate the battery life in hours of 3 brands of batteries. Now, the 3 brands of batteries are just descriptively brand 1, brand 2, brand 3. Now, before we can do an analysis, we want to go ahead and decide how we're going to do it, and we're going to be doing an F-test. Now, the F-test requires some arguments or information about the alpha value, the degrees of freedom for the numerator, and degrees of freedom for the denominator before we can get a critical F value. Now, the critical F value is going to act as a measuring tool whether or not we're going to reject the null hypothesis or not. So right now, to do the critical F evaluation, we're going to need to have an alpha. We're going to go ahead and use a 0.05 alpha, and our degrees of freedom for the numerator is going to be the number of brands minus 1. So for this example, we have 3 brands. 3 minus 1 is 2. So our first degree of freedom is going to be 2. Our second degree of freedom is the total number of observations minus the number of categories. So what we're going to do here is we're going to say, well, we have 21 total observations minus 3 categories. So our degrees of freedom for the second value is 18. Now, to calculate or find the critical F, we could go in and use an F table that is probably available in most statistics books, but I find it pretty easy to use the Excel built-in functions that are found under f of x. So that function is going to be FINV. If you type in FINV and locate that function, FINV, and just go ahead and click go. And here's our FINV function. It's the inverse F value. That's how we got the name. And what that value needs is it needs 3 arguments. First of all, the probability, and I'm going to click on that alpha value. Second of all, it needs the degrees of freedom 1, and I can click right on that value, which was 2. And I can click on the cell for the second degree of freedom, which was 18. Now, our critical F is going to be 3.55456. Now, to go ahead and do the ANOVA analysis, we're going to select some place to place the answers in our spreadsheet. I'm going to arbitrarily just choose A6. You can choose any unused cell so that you don't overwrite the data that you've already put into Excel. Now, you're going to go up and use the data analysis toolkit, and you're going to go ahead and select ANOVA single factor and click on OK. Now, for this, I'm going to go ahead and select the data range, and it's brand 1, 2, and 3, and all the way out to H4, from A2 to H4, and then I'm going to say that the data is arranged in rows. I do have a label in the first column, and I do want to use the 05 confidence level, and so we're going to put the output, and I'm going to select A6. So right here is the values that we need to enter into the ANOVA single factor method. Now, when I click OK, the answers are going to be propagated down the left side under A6, and right up front we're going to find that we have summary data. We have the 3 different groups or categories. We have the count in each one, the sum, the average, and the variance. Now that's interesting data. We could use it if we wanted to do manual calculations, but Excel is going to take care of all the calculations for us. So here is the ANOVA table, and the ANOVA table needs some explaining. First of all, down the left side we have the source of variation. We have between groups, which is known as the treatments, and within groups, which is known as error. Then we have the total. Now going across the top, the labels, SS is sum of squares, the DF is the degrees of freedom, MS is the mean square, F is the calculated F based on the data, the p-value is listed, Excel has already calculated that for us, and now we have the critical F. So going down through here under SS, we had between group treatments of 42 and a sum of squares of 416.571 for within groups. Adding those together gets the total. Now we find the degrees of freedom that we already discussed. Categories minus 1 is how we got the 2. Total observations minus the categories of how we got 18. Now the column here, MS, is just the sum of squares divided by the degrees of freedom. So 42 divided by 2 is 21. Same thing for the mean square for the treatments or within group, or excuse me, error within group. Now to get the calculated F, the calculated F is the mean square treatments divided by the mean square error, and that comes out to 0.90741. Now the p-value is calculated, and the p-value is 0.42, and that's what we're going to compare to our critical values. Now the F value, the F critical, is calculated here, and it's the same that we had earlier. Now to make a decision, we're going to look first of all at the F value. The F value had to be greater than the F critical. So we ask ourselves, is the F value greater than our F critical? And the answer is no, it's not. So as a consequence, we're going to fail to reject. We're not able to reject. So I'm just going to say fail to reject. Now, remember what our null hypothesis is. We're failing to reject the null hypothesis. We're rejecting the concept that all the values were equal for each of the batteries. So the alternative is at least 2 of the batteries are different, and we can go double check our answer by looking at the p-value. Now for us to reject, we had to have a p-value that was less than our alpha. Our alpha is 0.05 and our p-value is 0.42. 0.42 is not less than 0.05, so that's a second way that we could say that we're going to fail to reject. So these batteries are not all the same. there's at least 2 of them that are different. And if we were to look back at their data, we would look at, first of all, the difference between brand 1 and brand 3. And so that would give us a variance or an average of 44 compared to 48. So pretty much that brings us to a conclusion of the Excel analysis of variance.